Look at your hands. For roughly 200,000 years, every tool we built was entirely dependent on what those hands could do. We shaped flint into hand axes. We turned iron into plows, and steam into engines. But through every epoch of human invention, a simple truth remained unbroken: the tool was only as smart as the person holding it. A hammer never decided where to strike. A needle never chose the thread. A library full of books contained vast wisdom, but not a single page within it knew it was being read. Then, in the middle of the 20th century, we crossed an invisible threshold. We stopped building tools to extend our physical muscles, and started trying to build tools to replicate our minds. We took silicon, essentially purified sand, and passed electrical currents through it in patterns so intricate, so blindingly fast, that the line between simple calculation and actual thought began to blur. Today, artificial intelligence generates high-resolution art in seconds. It writes clean software code, translates dozens of languages in real time, diagnoses complex medical scans, and holds fluid, human-like conversations. Yet for millions of people using these systems every single day, the fundamental reality remains a complete black box. How did we get here? Are these systems truly intelligent, or are they playing the most sophisticated statistical trick in human history? To understand where this technology is taking us tomorrow, we have to go back to the moment humanity first tried to give a machine a mind. It was August 1956. While the world was caught in the Cold War and rock and roll was sweeping America, a tiny group of researchers met on the quiet campus of Dartmouth College in New Hampshire. Their leader was a brilliant 28-year-old mathematician named John McCarthy. Joining him were icons of early computing, Marvin Minsky, Nathaniel Rochester, and Claude Shannon, the father of modern information theory. They spent 2 months in a modest brick building, brainstorming over coffee, cigarettes, and reams of paper. They were united by an audacious hypothesis. They believed that every aspect of learning, or any feature of intelligence, could be broken down into such precise mathematical steps that a machine could be built to simulate it. It was McCarthy who coined the phrase that would define the next century: artificial intelligence. The mood in that room was pure mid-century optimism. These scientists weren't thinking about centuries down the road. They genuinely believed that a fully intelligent machine was just a few decades away. Marvin Minsky famously predicted that within a single generation, the problem of creating an artificial intelligence would be substantially solved. They assumed that because computers were already faster than humans at raw arithmetic, giving them common sense would be the easy part. They were dead wrong. The initial approach to AI was what engineers call symbolic AI, or rule-based systems. The strategy was simple: if you want a machine to understand the world, you just have to write down all the rules of reality into code. It sounded logical. But reality, as it turns out, is infinitely messy. Take something as simple as recognizing a cat. To a human child, identifying a cat takes no effort. But to program a computer using symbolic AI, programmers had to write strict, explicit logical instructions. If an object has 4 legs, fur, 2 pointed ears, and a tail, then it is a cat. But what happens when the cat is curled up in a ball and its legs aren't visible? What if it's a 3-legged cat? What if it's a small dog? Or a stuffed animal? Every time researchers solved one edge case, 1,000 new exceptions appeared. Human language and daily life aren't built on rigid mathematical rules, they are built on context, nuance, and unspoken understanding. The programmers were drowning in code, and the machines remained completely helpless outside of narrow, controlled environments. By the mid-1970s, the hype collapsed under the weight of reality. Investors pulled out. Governments canceled research grants. The field plummeted into its first major depression, known as the AI winter. Laboratories emptied, projects were abandoned, and for years, mentioning artificial intelligence on a grant application was a guaranteed way to lose your funding. The dream wasn't dead, but it was frozen solid. It would take a radical shift in philosophy to melt the ice. The breakthrough didn't come from forcing computers to follow human logic. It came when a small group of researchers decided to abandon top-down rules entirely. Instead of asking, "How do we teach a computer the rules of the world?" they asked, "How do biological brains learn without explicit rules?" A human baby doesn't learn what an apple is by reading a set of mathematical definitions. A baby sees hundreds of apples, touches them, drops them, hears adults say the word apple, and slowly, naturally, builds an internal mental model. This was the birth of true machine learning. Instead of hard-coding the answers, researchers began building mathematical structures called neural networks, loosely modeled after the interconnected neurons in the human brain. Instead of defining a cat, you feed a neural network a million photos of cats and a million photos of things that aren't cats. At first, the network makes wild, random guesses. But every time it makes a mistake, an algorithm adjusts the internal mathematical weights across its network, nudging it slightly closer to the right answer. Repeat that process millions of times, and something magical happens. The machine stops guessing. It discovers subtle pixel patterns, textures, and geometric ratios that define catness patterns so intricate that no human programmer could ever have written them by hand. The AI winter was finally coming to an end. But the real explosion was waiting for three crucial ingredients to collide: vast data, powerful graphics hardware, and a radical new blueprint for processing human thought. By 2012, two massive forces collided to create a big bang in artificial intelligence: the internet and computer graphics cards. For decades, neural networks lacked the data and processing power needed to scale. But the explosive growth of the internet provided unprecedented amounts of digital images, text, and audio. At the same time, computer scientist Fei Li created ImageNet, a massive database of over 14 million hand-labeled images. It was an unprecedented training ground. Meanwhile, researchers made a surprising discovery. The graphics processing units, or GPUs, designed to render fast, complex 3D graphics for video games, were mathematically identical to what neural networks needed. They weren't just good at processing one complex calculation at a time, they could perform thousands of tiny mathematical calculations simultaneously. In October 2012, a team led by Geoffrey Hinton entered a deep neural network named AlexNet into the ImageNet competition. It didn't just win, it shattered every previous record, reducing the error rate by a staggering margin. Deep learning was no longer a theoretical novelty. It was the undisputed future of computing. Yet, despite massive success in computer vision, human language remained an elusive fortress. Language is messy. Words change meaning based on where they stand in a sentence, who is speaking, and what was said 3 paragraphs earlier. Early language models processed sentences word by word, sequentially. By the time a model reached the end of a long sentence, it had often forgotten how the beginning connected to it. Then, in 2017, a team of 8 researchers at Google published a landmark paper with a strikingly simple title: "Attention is all you need." They introduced a brand new architecture called the transformer. Before transformers, a computer read a book like a child pointing at words one by one. Transformers allowed the computer to look at an entire page at once. Through a mechanism called self-attention, the model measures the mathematical relationship between every single word and every other word simultaneously. Consider this sentence: "The bank account was frozen because the river overflowed its bank." To an old algorithm, the word bank appears twice with identical spelling. But a transformer uses attention mechanisms to map the word frozen to the first bank, and river and overflowed to the second. It resolves ambiguity at light speed. This single breakthrough became the foundational engine for every large language model operating today. To understand how a large language model works, you have to realize something surprising: machines do not read words. They read numbers. When a transformer reads text, it translates every word, syllable, or punctuation mark into a token. Each token is assigned a position in a massive, multi-dimensional mathematical map called a vector space. In this conceptual space, words with similar meanings sit close together. King sits near Queen. Paris sits near France. But even more fascinating is that relationships become geometric vectors. If you take the mathematical position of king, subtract man, and add woman, the resulting point in space sits directly next to queen. When you ask a modern AI a question, it isn't pulling pre-written answers from a database. It is navigating this infinite multidimensional landscape, calculating probabilities, and answering a fundamental question: given all the text that came before, what is statistically the most meaningful token to place next? It is a next token predictor. But when you scale that prediction process across hundreds of billions of parameters trained on nearly the entire written record of human civilization, simple probability gives rise to something astonishing. While public attention remains focused on conversational chatbots and viral artificial art, the most consequential revolution is unfolding quietly inside scientific laboratories. For more than half a century, one of biology's greatest mysteries was the protein folding problem. Proteins are the micro-machines of life. Everything from your body's immune response to how your muscles contract depends on the precise, three-dimensional shape into which long chains of amino acids fold themselves. Determining the 3D shape of a single protein experimentally used to require months, sometimes years, of arduous laboratory work using X-ray crystallography. In 2020, DeepMind's AlphaFold solved this problem. In a matter of months, the system predicted the 3D structures of over 200 million proteins, virtually every known protein in biological science. What would have taken human scientists collectively millions of years to map was accomplished in a heartbeat. Today, researchers around the globe are using this open database to design target drugs for cancer, engineer enzymes that break down toxic environmental plastics, and neutralize novel viruses before outbreaks occur. AI is no longer just analyzing existing human knowledge, it is accelerating the discovery of new truth. Step outside the laboratory, and you will find that AI has quietly become the central nervous system of modern infrastructure. When you flip on a light switch, an AI system may be balancing the electrical grid in real time, predicting fluctuations in wind and solar output to prevent blackouts. When you order a package, machine learning models route thousands of cargo ships, planes, and delivery vans across global supply chains to minimize fuel consumption. In medical clinics, diagnostic algorithms scan mammograms and retinal images, catching microscale anomalies years before they become visible to human doctors. In agriculture, autonomous tractors equipped with vision systems spot-treat individual weeds with PR. Every powerful technology brings a shadow. And as generative models become exponentially more capable, we are confronting a crisis unprecedented in human history: the erosion of shared reality. For centuries, seeing was believing. A photograph, an audio recording, or video footage was treated as definitive proof that an event actually occurred. Today, generative AI models can synthesize photorealistic video, construct hyper-realistic voice clones from a 3-second audio sample, and generate convincing news articles at scale, for fractions of a penny. The threat isn't just that people will believe fake things. The deeper, more insidious danger is what security experts call the liar's dividend. When any piece of media can be effortlessly forged, bad actors caught doing something wrong can simply claim that real, authentic evidence is just an AI-generated deepfake. When trust in visual and auditory evidence vanishes, the baseline of objective truth begins to fracture. This reality crisis extends into the very systems we rely on for information. Because large language models are probabilistic next-token predictors rather than true factual databases, they suffer from a well-known vulnerability: hallucination. When a model lacks real facts to answer a complex question, it doesn't pause and say "I don't know." Instead, it generates plausible-sounding, grammatically flawless fiction, inventing non-existent court cases, historical dates, or scientific papers with absolute confidence. Furthermore, AI models do not exist in a moral vacuum. They are trained on text and images generated by human beings. That means they act as a high-powered mirror, reflecting and amplifying all our historical biases, stereotypes, and structural inequalities back at us. If historical hiring data reflects underlying societal prejudice against certain groups, an AI trained on that data will systematically replicate those same rejections hidden behind a veil of perceived algorithmic objectivity.